how did you get into becoming an astronomer? How did that all happen?
Yeah, right. So I was always fascinated by the night sky, and some of my earliest memories in Northern Ireland are looking out of the car window, driving in between, these sort of country towns. And that's the thing about Northern Ireland is there's a lot of cows, a lot of farms, and not a lot of streetlights. So you get these beautiful views of the stars. And I was always fascinated, wondering what they were. Face pressed against the cold glass of the car window, to get a better view, and that was fascinating to me. But it wasn't really. That was just one part of the things I was curious about. I was very curious about, the world around me, geology, all of these kind of amazing things. And then I read Stephen Hawking's Brief History of Time as a very precocious teenager. Maybe I think I was like 13 or something.
Whoa.
I tried to read it.
That's a record as well.
Oh, man, I did not understand most of it. And in fact, I reread it recently on his passing, and I was like, man, I really did not get much of that at all.
Yeah. Still don't get it.
No, yeah. So that was enough for me to realize there were bigger and more fundamental questions out there. And that you could actually have a job in asking those. That was something that just blew my mind. So it really wasn't until going into university that, I took physics at University of Manchester, and there's, Brian Cox floating around, and that was pretty cool. And that was the beginning of my realization that, I might be able to do this as a job. This is crazy. But I couldn't choose. Like, I couldn't settle on any specific physics topic, so I picked cosmology, which is literally the study of everything, the study of the universe. And slowly over time, kicking and screaming, I've been focusing ever more on a specific question of dark matter. This invisible stuff makes up 5 times more of the universe than everything we can see put together. We still don't know what it is. I suspect we'll know in the coming 5 years.
Really?
Only because if we don't, our detectors hit a fundamental barrier.
It's all or nothing.
It's basically all or nothing, and then we have to have an entirely new technological approach.
Really? So
which
it's
will
like
set
you
us
have
back.
to scrap everything. If this system doesn't work, then you've exhausted this system of discovery, and you have to start again. Basically, is that
that's basically it. We're looking at what are called directional detection. So in other words, we are there's this constant hurricane of dark matter just streaming through us as we speak. So this is the idea that the galaxies are held together, gravitationally speaking, by this massive cloud of dark matter. It's matter because it's got gravity. You can quite literally see the stars and gas of the galaxy pulled in strange and unexpected ways by this invisible gravitational partner. The stars are getting whipped around in ways that are just not explainable in any other sense. But it's dark because we can't see it. So there is this cloud of dark matter, and we know that our sun is going around the galaxy. And this gives a headwind effect where, familiar to anyone who's driven through the rain, as you're driving, the rain is falling vertically. And yet, especially visible at night when you've got the car lights on, it's just at that last second, it looks like that falling rain just whips towards the window screen, right, at great speed. Now, of course, that's you going through it. And in the same way, our sun is going through the dark matter cloud of our galaxy, meaning this dark matter is whipping towards us at the speed that our sun has traveled through it. So we're looking for this dark matter headwind. Now, if we don't find it in the next 5-10 years, and this is essentially the next generation of these detectors that wait, sitting underground, protected from other things that can bash into them, like radiation from space, these detectors essentially wait to be struck by the dark matter. Now, if they don't see it, if these detectors, if we have to continue to build them bigger, more sensitive, wait for this ghost-like dark matter to finally collide, sooner or later they get big enough that they actually see the particles we call neutrinos coming from the sun. So this is a lot of physics, but basically
doing my PhD in 30 seconds.
Yeah. Basically, we know if we don't see the dark matter in the next few years, if we have to build our detectors bigger again, because essentially this ghost-like dark matter can travel through us, travel through solid walls, travels through the Earth, or like collision. Hopefully, very occasionally, it will collide with an atom of our body, for example. You'll never have noticed that, but we make for very bad dark matter detectors. That we're building these better ones. if we don't detect that, then the sun is producing these neutrinos, which are very similar sort of ghost-like particles. We will be blinded by that. In other words, our detector will be so big, we'll be detecting the sun even when we're at the deepest cave imaginable, even protected from every other source of radiation from impact. To isolate our experiment, the sun will be blinding us from underground, traveling through the entire Earth, its particles. So that's where we're sort of, this is our nightmare, that if we don't get the dark matter in the next 5 to 10 years, this current generation of technologies, our detectors will be blinded by neutrinos from the sun. So it's a tricky situation. We're sort of getting to the end of a near 40, 50-year quest. And if we don't get it this time, we will have to basically develop a new technology path that can distinguish these neutrinos from the dark matter. And that will cost probably another 5, 10 years. And at that point, I'll be like, oh my God, I'm going to be 50 or 60.
I'm moving on, guys.
Oh, I'm out of here. I'm tapping out. So,
right.
You know, for very personal reasons, I want this to be discovered, and I want it to be discovered soon.
Yeah, absolutely. I feel like you must feel the same way as the guys at like SETI, you know, they're just always cracking away trying to find you know, intelligent life. Let me just ask one question, because when you were talking there, because I pride myself on asking the questions that my listeners are thinking.
Sure, right.
Because our listeners are not astronomers, I'll be honest with you.
That's cool. I probably went too deep too quick.
No, it's all right. It's all good. So, but you talked about the dark matter headwind that you can see when the Earth is basically pushing up against it. Not at the Earth, the sun is pushing up against it, and you can see the pull of the dark matter, or that the resistance, I should say. How can you see a resistant force pushing on the sun, or the sun pushing into it, without detecting it fully? Like, how does that work?
Yeah, right. So we have this this invisible cloud of dark matter, some kind of new particle, right? We just do not know what it is. But again, there's absolutely staggering amounts of it that can hold the entire galaxy together. So as our sun is moving through this cloud, we will the entire solar system is going in the same direction, you know, the Earth as well as the sun, and we'll see a headwind effect. So at this stage, this isn't saying anything about what the particle is, if it's bumping against us. We just know it's rushing through us, or rather we are rushing through it, just like we're driving through the rain. So what we hope is that very occasionally the dark matter, rather than flying between and indeed even within the atoms of your body, never colliding with the particle itself, the center of the atom we call the nucleus. That's a tiny target. That is, we think solid matter is solid, right? I mean, you know, I'm touching a table. I can feel the chair pushing back on my legs as I sit in it, right? I'm not falling through it. But that sensation of a solid table or a solid chair is no physical contact between the solid particles. It's actually the repulsion.
It's funny, isn't it?
It feels solid, right? You can tap it, right? But we know that it's actually the cloud of electrons around the atoms in the table are repelling the electrons in the atoms in my finger to give that sensation of being solid that I can't push through. Now, if you don't care about electrons, electric fields, if you're this dark matter that just doesn't see any of that, then actually solid matter presents a very small target. It is anything but solid. There are gaps in solid matter, if you don't care about these electrons, are essentially everything. The nucleus is a very small target, which is why I can have 100 million particles a second go through just my eye from this dark matter. And I will never see any of that collide. It will quite literally never hit one of the atoms and reveal itself. So we have to wait, because sooner or later a particle will collide with the nucleus. At that point, it sends the nucleus, the center of our atom, reeling away. And that will give a little flash of light. Certainly will if it hits one of our detectors. So what we're looking for is this very occasional collision as a ghost-like dark matter particle slams straight into the center of the nucleus of an atom. And that's That's an insanely small chance of happening. You can wait for days, weeks, years at this point for that to happen. So the moment it does, that will open the floodgates. I mean, that will be the Nobel Prizes will be handed out at that point.
It's like the gravitational waves, basically, that was just waiting for that one stretching of the, forgive me if I'm wrong, stretching of the space.
Yeah.
The stretching of space, I guess.
Yeah. And that was, but just a tiny. I mean, my God, I think, we have a hard time in dark matter studies. Gravitational wave. I mean, the stretching was equivalent to a 10,000th the size of the nucleus. This tiny thing I'm talking about, and it's 10,000 times smaller than that.
That's hard to actually comprehend as
the way you comprehend it is, which is no easier to be honest, but it's the distance. It's a hair width change in the distance between our sun to the nearest star. And we saw that hair width.
Oh, geez. How good science.
So
far
good.
out.
So good.
What is going on? That is insane.